Rates of change and behavior of graphs. Since functions represent how an output quantity varies with an input quantity, it is natural to ask about the rate at which the values of the function are changing. For example, the function c of t below gives the average cost in dollars of a gallon of gasoline t years after 2000. If we were interested in how the gas prices had changed between 2002 and 2009, we would compute that the cost per gallon had increased from $1.47 to $2.14, an increase of 67 cents. While this is interesting, it might be more useful to look at how much the price changed per year. You are probably noticing that the price didn't change the same amount each year. So we would be finding the average rate of change over a specified amount of time. The gas price increased by 67 cents from 2002 to 2009 over 7 years, for an average of 67 cents divided by 7 years, which is approximately $0.096 per year. On average, the price of gas increased by about 9.6 cents each year. Rate of change. A rate of change describes how the output quantity changes in relation to the input quantity. The units on a rate of change are output units per input units. Some other examples of rates of change would be quantities like a population of rats increases by 40 rats per week, a barista earns $9 per hour, a farmer plants 60,000 onions per acre, a car can drive 27 miles per gallon, a population of gray whales decreases by 8 whales per year, the amount of money in your college account decreases by $4,000 per quarter. Average rate of change. Between two input values is the total change of the function values, output values divided by the change in input values. Average rate of change equals the change of output divided by the change of input. Example 1. Using the cost of gas function from earlier, find the rate of change between 2007 and 2009. From the table in 2007, the cost of gas was $2.64. In 2009, the cost was $2.14. The input, years, has changed by 2. The output has changed by $2.14 minus $2.64, which equals negative 50 cents. The average rate of change is then negative 50 cents divided by 2 years, which equals negative 25 cents per year. Notice that in the last example, the change of output was negative since the output value of the function had decreased. Correspondingly, the average rate of change is negative. Example 2. Given the function g of t shown here, find the average rate of change on the interval 0, 3. At t equals 0, the graph shows g of 0 equals 1. At t equals 3, the graph shows g of 3 equals 4. The output has changed by 3 while the input has changed by 3. Giving an average rate of change of 4 minus 1 divided by 3 minus 0 equals 3 over 3, which equals 1. Example 3. On a road trip, after picking up your friend who lives 10 miles away, you decide to record your distance from home over time. Find your average speed over the first 6 hours. Here, your average speed is the average rate of change. You traveled 282 miles in 6 hours for an average speed of 292 minus 10 divided by 6 minus 0, which equals 282 divided by 6 equals 47 miles per hour. We can more formally state the average rate of change calculation using function notation. Average rate of change using function notation. Given a function f of x, the average rate of change on the interval a, b is the average rate of change equals change of output divided by change of input, which equals f of b minus f of a divided by b minus a. Example 4. Compute the average rate of change of f of x equals x squared minus 1 over x on the interval 2, 4. We can start by computing the function values at each endpoint of the interval. F of 2 equals 2 squared minus 1 half, which equals 4 minus 1 half, which equals 7 over 2. F of 4 equals 4 squared minus 1/4 equals 16 minus 1/4 equals 63 divided by 4, or 63/4. Now computing the average rate of change. Average rate of change equals f of 4 minus f of 2 divided by 4 minus 2 equals 63/4 minus 7 halves divided by 4 minus 2 equals 49/4 divided by 2 equals 49/8. Example 5. The magnetic force F, measured in newtons, between two magnets is related to the distance between the magnets d in centimeters by the formula F of d equals 2 over d squared. Find the average rate of change of force if the distance between the magnets is increased from 2 centimeters to 6 centimeters. We are computing the average rate of change of f of d equals 2 over d squared on the interval 2, 6. Average rate of change equals f of 6 minus f of 2 divided by 6 minus 2. Evaluating the function, f of 6 minus f of 2 equals 6 minus 2. 2 over 6 squared minus 2 over 2 squared divided by 6 minus 2, simplifying. 2 over 36 minus 2/4 divided by 4, combining the numerator terms. Negative 16 over 36 divided by 4, simplifying further. Negative 1/9 newtons per centimeter. This tells us the magnetic force decreases on average by 1/9 newtons per centimeter over this interval. Example 6. Find the average rate of change of g of t equals t squared plus 3t plus 1 on the interval 0, a. Your answer will be an expression involving a. Using the average rate of change formula, g of a minus g of 0 divided by a minus 0, evaluating the function, a squared plus 3a plus 1 minus 0 to the second power plus 3 multiplied by 0 plus 1 divided by a minus 0, simplifying. A squared plus 3a plus 1 minus 1 divided by a, simplifying further and factoring. A multiplied by a plus 3 divided by a Canceling the common factor a plus 3. This tells us the average rate of change between t equals 0 and any other point t equals a. For example, on the interval 0, 5, the average rate of change would be 5 plus 3 equals 8.